pace model, um, or TensorFlow and different types of that. We have different checkpoint converters to compile into the faster transformer format. That's what you'll be doing in the lab today. So you'll be pulling, I believe, a Hugging Face model, converting it into a faster transformer format, and then deploying it across multiple GPUs. As you see there on the bottom left, you have some different data types. Top right, in terms of features, you get more or less multi-GPU and multi-node inference out of the box. And essentially, when you go to do that, you have to compile the model. Let's say I'm deploying on 4 GPUs. On a single node, I have to compile the model on 4 GPUs for that node. Versus if I want to deploy on 6 GPUs, I would compile that model down to 6 GPUs as well. And we have support for the major frameworks. And if anyone is a C++ guru, you can always get as low level as you want. Some other optimizations here, some are model specific. The main ones are fuse kernels for frequently used operations. For autoregressive models, there's, I think, faster beam search. Yeah, so it's very, very fast beam search implemented in C++. So as you generate tokens and you try to figure out, hey, what's the best, maybe not what's the most popular token or probable token, but what's the best sequence of tokens in terms of probability, those things work a lot faster. And that's what, for instance, like Mosaic, I don't know if you're all familiar with the company Mosaic that got acquired by Databricks, so like 1.2 billion, they leverage faster transformer on their inference platform as well. So a lot of folks are using this behind the scenes, and they have some good public benchmarks on that. And in this, what we're trying to look at the top, all of the white spaces mean that the GPU is essentially idle because there are, I think, approximately 50 different kernels running. And then after you compile to the faster transformer format, essentially you just see 14 kernels running. So we'll combine a bunch of different operations that you have internally happening inside of your model to try to just get less kernel calls to the GPU, and you're just doing more operations per unit call. Okay, Triton Inference Server. This is an open source enterprise supported project from NVIDIA for doing inference. So if you're doing literally any type of inference, all of our models at NVIDIA are sort of pushed out on Triton, and sort of the hallmarks there are, let's see. So the way that it works, you have a Python or C++ client. You communicate through HTTP or gRPC, and you essentially have a lot of support for different model types or different backends. So the idea here is if you have a TensorFlow model, Onyx model, PyTorch, TensorRT, they all deploy the same exact way. This works both on CPU and GPU. So this is a nicer chart. So you can see some of the major frameworks that we support. And then, for instance, like TensorRT LLM is another backend from NVIDIA. So that'll just be a, back in here. As I mentioned, you can deploy both on CPU and GPU. So we have some things. Yeah, we could probably walk through some of the flags in Triton as well. Yeah. And when you go to deploy Triton, it's a container, so you can deploy it anywhere. One of the cool things, if anyone is doing any type of XGBoost inference, we wrote a CPU library and a GPU library that are much faster than the sort of XGBoost open source project, so you can leverage that to scale up XGBoost. I think, to me, one of the most impressive features of Triton, so you have these different types of querying types, but what's very interesting about the ensemble model is that you can create a multi-framework ensemble model, meaning I can do pre-processing in PyTorch. I could probably do one level of inference in TensorFlow, another step if I had a PyTorch model, and all of that is viewed as a single unit or single model type inside of Triton, right? And all that's managed through configuration files. And lastly, depending when you go to deploy, and you have different types of query types or query patterns, dynamic batching is a thing where you can wait a very, very small period of time to accumulate requests coming in, so you can push larger batches into the GPU. Okay, but here's an example of model ensembling that you might leverage. You're going to leverage an ensemble model today. So I'll have all of this top processing logic executing on the CPU, and then these two models get executed on two separate GPUs. And in the config file, you can actually specify which GPUs you want to deploy on, and actually which parts of the model they're going to deploy on. And that's what you'll end up doing in today's lab. So you're going to end up creating this pipeline. So I have some input text coming in. I have two different GPUs, and now I'm splitting the model across two different GPUs. If you had 6 A100, this is how you would split up the parts of the model, more or less like that in a configuration file. Okay, here's an interesting trick that some of the researchers here at NVIDIA leveraged. So they were deploying a larger model. So what you end up doing, you basically merge all of your checkpoints. We have this thing called Onyx Graph Surgeon, so that if you go into, you put your model into Onyx Graph Surgeon, you could actually see all of the different layers that exist inside of your model. And from there, you can actually split your model up into different pieces.
Link
so when you split the model up into
established.
different
Mic off.
pieces, you're essentially just making it, let's say, one big model into 4 small pieces. You optimize each of those pieces in TensorRT. So that means each of those pieces will have an optimized engine, and then you deploy all of those pieces leveraging the TensorRT backend and an ensemble model. So imagine I was splitting up a model across 4 GPUs. Okay? And this is a more intentional implementation. So someone mentioned maybe some of the flags in Triton. The main thing I would like you to get comfortable with is what some of the configuration files look like. So here I have a model named Megatron GPT-3. I think it's an 18 billion parameter ensemble. I'll have my inputs coming in. So the way that Triton works is you'll name your input, you'll specify its input data type, and then you specify its shape, because Triton goes off a tensor in, tensor out type paradigm. And for each of these submodules, you'll have, you can essentially map the inputs and the outputs to specific parts of the model. I think you have a different one here. Yeah, okay. So here you're seeing 2 different models being combined in this ensemble scheduler here. And you've seen the corresponding inputs coming in, the corresponding outputs, and in addition, which GPU it's actually running on. So this is where you get to specify which GPUs. And this other parameter that's not necessarily highlighted, this count. So if I wanted to run 2 copies of these models across GPUs, I would increase this to 2, increase that to 2, and now I have 2 model copies. So essentially twice the amount of throughput that's running. And if I wanted to put these on CPU, I would put kind CPU and kind CPU, and that's how you default a model back to CPU. Okay. We're going to take a look at GPT-3 Megatron LM example. This is one I think you might be, you're going to use GPT-J in the lab itself. That's a good question, Rafa. So the question is, are these different models or different parts of the same model? In this case, it's different parts of the same model. So I take all of these checkpoints, I'll split them up, create optimized engines for each of them, and then essentially deploy each component of the engine. In this example, I'm just deploying 2 parts of a model and really trying to call it as one. Let's see. Oh, here's an interesting case. So you might come into this scenario where, okay, I want to use a DGX A100, just like what we're doing in class. But hey, I'm not going to use all 8 GPUs. I might want to leverage different GPUs for different jobs. So what you can end up doing is you can specify a different number of copies of each of those models. So in Triton, I can either have these as 4 distinct different models, and let's say each model was split across 2 GPUs. So this could be let's say a computer vision use case, an NLP use case, something else. I'm just giving a quick example. Or these could be 4 copies of the same model, right? And as you can see, each model is split across multiple GPUs, and this is what Triton gives you the ability to do out of the box. In terms of throughput, naturally, the more GPUs that you leverage, the higher throughput that you can get. And for latency constrained environments such as search and things like that, we see a lot of people starting to focus on using GPUs because you can put more powerful model and still maintain your latency budget by doing some of these optimizations. Another thing that ends up happening as well is with TensorRT, we're always updating TensorRT. In this case, we were using Onyx runtime. I think I'm not, yeah, we're using Onyx runtime here. And if you compile a hardware specific, I repeat that, a hardware specific inference engine, that is by far the best way to get the best performance, especially on our hardware. Let's see. Okay, yeah. In terms of different sizes of models, you can run these things on really, really large models. This is what, once again, we use for all of the inference work here at NVIDIA. And with all the other customers that we work with, very large customers as well. So here's what it kind of looks like at a higher level in terms of an overall architecture. Once again, you have your client. In terms of Triton, you have a bunch of different, call it like scheduling options. You know, in terms of model copies, the delay that you wait to accumulate batches. And then you have this thing called a backend. So remember, a backend is either PyTorch, TensorFlow, etc., etc. So once you compile a faster transformer model, you'll use the faster transformer backend to interpret that model to then serve it to production. Okay. And here's kind of what you're going to walk through in class. So first, are you going to clone the faster transformer backend? From there, you're going to build to get Triton to be able to understand how to use a faster transformer model. Sorry about that. Yeah, you'll clone the faster transformer library from there, and you will pull down the model weights for I believe it's a GPT-J model, and then you'll actually run the faster transformer scripts to compile it on your 4A100. I think we deploy on, I can't remember if you deploy across all four or just two of them. And then you run this thing called kernel auto-tuning, because it'll have to figure out, all right, I'm using these two GPUs. Instead of using one, I'm using two GPUs. What's the best way to optimize these kernels to launch across the GPUs? Okay. And then in that process, you're going to create this ensemble model. So the ensemble model, if you kind of go through it, it'll be a file, basically a set of files. So it's going to host, you'll see a set of logic for pre-processing. This is saying, okay, I have some input data coming in. Here's the model that's doing pre-processing. You'll have this model, it'll have two files. One will be split on GPU1, one will be split on GPU2, and then you have a post-processing module. So you'll essentially have four individual model files, and then you'll have a fifth one that combines all of them. So hopefully that makes sense at a high level. It makes sense. It'll make more sense once you get into the project itself, and then you hopefully get to see, you know, a lot higher throughput. That graph is not very useful. Let's see. Yeah, these are just some inference benchmarks. But what I wanted to, yeah, so in the lab, you're basically going to run through this. So go ahead and launch this second part. You can go ahead and shut this piece down for the first one. And if you start the second one, I think it should shut down the first one. Make sure you download the slides as well. I could always send you the version that I have. Another thing I wanted to show you is the Triton repo. I think this is important as you, okay. Hopefully everyone, can you just put a +1 in chat if you're still mentally with me? I want to make sure. So like I was saying, great. So this is what we use to deploy all models at NVIDIA. It doesn't have to be deep learning models. It could be anything. So if you want to deploy Llama 27B, here's a tutorial for that. But the main thing I wanted to walk through, let's see if we go through this. This has really nice documentation. Okay. So model deployment. So the main thing, if I look at this thing called a model repository, so the way that Triton works is it's a container. We have a very specific, let me see if I find the format of it. Yeah, so we have a very specific format. So that we have this thing called a model repository, and then inside of there, you're going to put the name of each model. So a folder for each model. Inside of that folder, you're going to have a version. And inside of that version folder, you're going to have the actual model file. Inside of the actual model folder, you'll have this config file. This is basically all of the configs that you can do with Triton. And in this case, in this example, I have two models, a text detection and text recognition. They each have a version of one, and then they each have a corresponding configuration file. So when I launch Triton and I point to this folder as a model repository, Triton will detect, hey, I have two GPUs, and then I'm going to configure each of those GPUs based on what's in this config file. Now let's take a look at the config file. For text detection, you choose a backend, so what type of model are you running? In this case, we're running an Onyx model, so we run it with the Onyx backend. It's often best practice to specify a max batch size, so this will, yeah, I'll send the link. Let me just put this link in the chat. Yeah, these are really nice tutorials to go through. Literally, like you could deploy more or less any type of model, and this thing scales very well. For instance, every time you use spell check on Amazon, you're using this. Okay, so I'm specifying some inputs. So I have some input images coming. They have type FP32. When you use -1, this is saying that dimension is not specified. So I can get, in terms of batches, so it's usually batch and then your next 3 dimensions. And then I have some output coming out, and you typically specify those dimensions. And that's more or less it. This is for in terms of inputs and outputs. When you launch the Triton server, so when you launch your server today, hopefully you see the output, you'll see that those models are ready. And that means I can start serving requests to the model, right? So any way that you have a Flask application, you can literally just rinse and repeat this quite easily. And the other thing, let me see. 1 second. I come here. Okay. I just kind of want to walk through this very quickly just so that you at least get to see this while we're on the call. So if I wanted to do dynamic batching, this means I want to wait 100 microseconds in order to accumulate requests, okay? Because oftentimes you might have a different set of requests coming in. And in terms of throughput, if you process each request as they came in one at a time, you don't get a lot of throughput. So by waiting a little bit, you accumulate more of a batch to send more data to the GPU, because the GPU just likes a lot of data. Concurrent model execution, this is just you having multiple copies of the model. So I would literally copy this, copy paste it into my config file, and this is the number of model copies that I have. If I wanted to run 100 copies of a model, I could literally change that to 100, and now Triton will spin up all 100 copies, split across these 2 GPUs. Okay. Okay, I think the other last thing, yeah, those are the 2 main things. You do get some tools in terms of, we have this thing called Proof Analyzer, so you can basically send a ton of requests to Triton across different concurrency ranges, and you can get some throughput. This is a tool that you'll be using today. So you get a bunch of throughput and latency values coming out at each concurrency level. Okay, if you don't have any questions, go ahead and jump into this part of the lab. So this should, make sure and download those slides. And then once this comes up to launch, it should be good to go. Let's see. Yeah, and if you go, so in terms of the other part, I wanted to make sure. Okay, so model ensembles as well. You can see how you can push things back to the CPU or GPU depending. So you can build different configurations of models. I'm just waiting for my thing to load. But yeah, this entire tutorial will walk you through on how to do all of those things. So if you are deploying like seriously any type of LLM application, and for Llama 2, we do have some good examples on that now. So if you look at this, or Falcon 7B, yeah, you can go ahead and pull this. Let's see. Okay, I'll be in chat with any questions. Just gonna go grab some coffee quick. So Tibbs, go ahead and when this thing's not this one. Okay, this is spun up. Taking its sweet time. Yeah, go ahead and run. Go ahead and go through these 4 labs. And then once you actually populate the lab and go through labs, you'll see this model repository get filled up, and you should see the same structure. And in terms of how much time, excellent question. Yeah, we more or less have. Let's go for an hour and see how far you get. But we have from now until 5 or 6 for you to finish. So go ahead, and this is the last hands-on section. Then you move to the assessment if you got through it in time. Do this. Oh, so if you are seeing the Jupyter Lab notebook from the first section, go back to, sorry, I'm not showing my screen. Share my screen. So if you want to get to the lab, you want to come back here, go to model parallelism, go to inference of large language models, and it should bring you to this section. And then you see a thing called start. You hit start, and that should run. Sometimes when this thing, so before you actually, this is probably a good time to take a break actually. So maybe take a 5-minute break, because when you launch this instance, it would have launched in the cloud, but there are a ton of files that we got to download. So sometimes when you go to run the lab immediately, those files would not have existed on the machine yet. So if you can maybe restart that lab and run it again and see if those files came in. Especially if it's weights, it'll take a little bit to download sometimes. So just wanted to point that out. Can someone just let me know if they see the updated time that I posted on this active whiteboard? I think it should say 4 p.m. Perfect. Thank you.